welcome back to another Houdini tutorial from 9between, and in this tutorial we'll be going over a bunch of the different nodes that you can find in Houdini. Mostly in this one we'll be going over the attribute nodes, and this is going to be a bit different. Instead of the usual step-by-step where we show you how to create an effect, we'll just be explaining some nodes. So, hope you enjoy. In Houdini, as per usual, let's just go ahead and drop down a geometry node, dive inside, and we'll begin with let's begin with one of the simpler attribute nodes. Let's begin with attribute blur. So drop down an attribute blur, and let's give it something to work with. So above it, let's just drop a sphere, change it to a polygon mesh, and then we'll drop an attribute wrangle, plug your sphere into the attribute wrangle, and then we'll just say if at p.y greater than 0.5, then change the color. So we'll make it set the color to, or rather at cd equals set 1, 0, 0. And then we'll just make the rest of it black. So else at cd equals set 0, 0, 0. So black. And so we end up with that. So let's just plug that into our attribute blur and set our display flag. So as you can see, our sphere shrunk slightly, and the reason for that is this attribute that we're currently blurring. So we can choose which attribute we'd like to blur. Currently it's blurring position, and so it's averaging out all of the points' positions. So we can change this to CD. And if you take a look over here, our step size defines how big of an area you would like to blur along. So it may be easier to notice if you increase your rows and columns on your sphere. So let's go to rows and columns and make it 50 by 50. Go back to our attribute blur. So if we increase our step size slightly, so let's go to 1, and then push up the iterations, you can see that our red attribute blurs. And it's quite a smooth blur, and it does a decently good job. So, there's not much to really show in the attribute blur node. So next, we'll drop down another attribute blur, because I'd like to show you what this influence type does. So let's plug in a rubber toy. So set your display flag on the attribute blur, and we'll keep this attribute as p. We'll increase our step size to 1, and then we'll just blur it. And that looks quite tragic. But what this does is each connected piece, because of our influence type, is being blurred. So for each connected piece, we're blurring its p attribute, which is the position. So as you can see, it's more or less finding the average of the positions. But if we change this to proximity, it no longer works with connected pieces. And now we have this where it finds the average between points that are close together. So you can choose the radius and how many neighbors you would like to affect. So the neighbors, that's just how many points it's sampling. So if we drop it all the way down, it samples very few points. But if we push it all the way up, it samples a lot of points. And this proximity radius is just how far from each point it looks for neighbors. Alright, so let's go on to a more interesting one. Let's just drop down a sphere, make it a polygon with a frequency of 10. So we end up with this. And let's just duplicate this, and then also drop a box. So this box will scale up a bit, make this 1.5, polygon mesh, with axis divisions of 10 by 10 by 10. Alright, so let's drop a switch node, and this node just swaps between inputs. So we'll plug our sphere and our box into there. So as you can see here, we can change which input is being viewed. Next thing that we'll do is we'll just drop down an attribute wrangle. And actually, we can just use the one from before. So just take this one on the side, Control C, Control V, and plug it in over here. Next, we'll drop down an attribute copy. And into the first input, we'll take our sphere. Into the second input, we'll take this attribute wrangle. So just go over here to your attribute copy. Now, as you can see, currently what we're doing is we're adding color to whatever's coming out of our switch. And on the original sphere, we don't have anything. But do keep in mind that this sphere and this sphere have the same topology. So when we use this attribute copy, it's copying the attributes from this sphere onto this one. And it's copying it based on topology. So the issue with using an attribute copy, although useful, is that if we change what type of geometry we want, so say we change to the box, right, now we have this box with the red top. If we try to copy the attribute from the box onto the sphere, it does this. And the reason is because we don't have matching topology. Much like when you use a blend shape, you have to have matching topology. This you also have to have matching topology. It doesn't work based off of proximity, so you can't just, share an attribute from one geometry to another. So what would you do if you would like to actually just share one attribute from one geometry to another, even if topologies are different? Well, that's what attribute transfer is useful for. So let's drop down an attribute transfer. And over here, we can just duplicate this whole setup over. So just holding Alt, just click and drag. And there we have it duplicated over. So remove this attribute copy, plug your sphere into the first input of the attribute transfer, and your attribute wrangle into the second. So now, as you can see, we have this box that has red at the top. We have this sphere that has no color. And then we're attribute transferring based on proximity. And by default, it will copy your color attribute. So it may not show anything over here, but it's actually copying your CD. So, putting that in doesn't change anything because it automatically does that. But if you add something else like, N, then it will only transfer N and it will remove the default of CD. So we can put CD in for now and go over here. If you take a look over here, we have these settings. So we have distance and we have the kernel function. Now, the kernel function you don't really need to worry about. It's basically how it determines the point at which to transfer attributes. It's based off of a metaball model where proximity defines how an attribute is transferred, but really you're probably not going to ever use a different kernel function. But over here, on our distance threshold, we can define how far an attribute is transferred from. So if you want, very accurate transfer, then you would drop your distance threshold. So clearly we have this cube coming in and it's not the same geometry as our sphere, right? We can template this and see. So we can actually change the distance threshold on this to like 0.1 and you end up with that sort of weird thing going on. So distance threshold just defines how far an attribute is transferring. How far should we look before we transfer this attribute? So we can also find areas outside of the distance threshold to blend with, and that's what blend width is used for. So if you push that up slightly, you can see that these attributes are still being transferred. And if you increase the sample count, you end up with a more accurate blur. And so that sort of sample count works similarly to the blurring iterations on your attribute blur node. And if I'm not mistaken, I do believe they use a similar model, the attribute blur and attribute transfer node, where they average out, a transfer. So that's all there really is to know about this. We use this quite often, and all of these nodes I'm reasonably certain you've seen before. So we can go on to something a bit more complicated. And let's go ahead and create another sphere. Change it to a polygon with a frequency of 20. Set your display flag and you end up with this. So let's say you would like to create some sort of dimpling effect on a sphere so it doesn't look smooth. Well, you could do that by affecting geometry, so adjusting point positions, or you could do that, kind of fake it by adjusting normals. And there's a really nice way to do it. So let's just drop down a normal node and set it to points. So if we go over here, we can take a look at our normals. So we have all of these normals just, pointing off of the sphere, as you'd expect it to look. Next, we can go ahead and drop down an attribute randomize. And this is where it gets quite interesting. So at the moment, by default, it's randomizing the CD attribute. So over there you can see which attribute it's randomizing. So it's randomizing CD. So let's just change that to N. So it may look quite weird right now, And the reason for that is because of the direction of our normals. Now, as you can see here, it's randomizing a value, right, for our normals within 3 dimensions. And these are the values that it's fitting it between. So all of our normals are between 0 and 1 in, the x, y, and z in the x, y, and z direction. So we can change the way that it distributes, because we don't want it to be in a direction. We want it to just sort of, be surface-based. So we can change this to direction or orientation. And then we can activate cone angle. And so cone angle defines what sort of cone away from the shape you're creating. If we push this up a bit, you can see that the code widens and opens. So it looks a little bit crazy right now, and it looks over the top. And the reason is, it's because it's actually just setting the value, right? We would like to add it to our existing normals. So to do that, we can just say add value. And now you may look at this and feel like it's too much. And that's where global scale comes in handy. You can just drag this down slightly and reduce the amount of randomization that you're adding to your existing value. So as you can see, as it was before, it was smooth, and now it's got slight variation on it. So we can just hide that, and all of a sudden we have this dimpled effect. And if you look from the side, it's still perfectly smooth. But what we've done is we've faked a bump, and this is what normal maps do. So that's just something interesting you can do with an attribute randomize node, but you can do loads of things with this, and it's one of the more useful nodes to know. So let's keep going, and let's see, what should we try out next? Let's just drop down a box. Once again, we'll make it a polygon mesh. Give it a scale of 1.5, and we'll do 8 by 8 by 8. Alright. So let's drop down an attribute wrangle. And once again, if at p.y is greater than 0. Let's do 0.4 this time. Then at cd equals set 0, 0, 1. So we'll make the points blue. Great. And actually let's just add an else statement. Once again, we'll just make all the other points black. At cd equals set 0, 0, 0. So now we have those points that are blue and these points that are black. So this is a great time to show how an attribute promote works. So attribute promote, it's a node that's used quite often. And as you can tell from the name, it promotes an attribute. But what does it promote it from and to? Well, it promotes it from, point or vertex, or detail, as you can see here, to another class. So we can go from point to primitive, or from primitive to point, or primitive to vertex, whatever we need. Alright, so currently, if we open our geometry spreadsheet, you can see that our color attributes are on the points. So what happens if we would like it on the primitives? Well, that's where the attribute promote comes in. So we can go from point to primitive, and the attribute that we would like to transfer is cd. And as you can see, it went from being faded between these two to being solid. And the reason is, it takes the average of those points that were blue and those points that were black and gets a middle ground and sets it for the whole primitive. So what if we don't want it to be an average? Well, that's exactly what this promotion method is for. As you can see here, we have maximum, minimum, average, mode, medium, and all of the rest. So if we set this to maximum, it'll take the highest value and set it for the whole primitive, right? So instead of averaging it out, it'll just take the highest value and set it for the primitive. So it searches on this primitive, what is the highest value for cd? And then it says, all right, I found the maximum, it's that over there, I'll set it for the whole primitive. Now you can do the same with minimum, and it finds the lowest value on the primitive and sets it for the whole primitive. So we'll set this back to maximum, and now you can see the difference. It goes from being that faded over there because we have some points being blue and some points being black with an average, to being a primitive attribute. And you can check over here in your geometry spreadsheet, it's gone from being a point attribute to a primitive attribute. Alright, so we can move on from there. And we can actually just duplicate this over. Can delete this attribute promote. So this is something that you don't see used very often. And honestly, I don't use it pretty much ever. But it's useful to know because sometimes you'll be looking for something like this and, you know, this just gets the job done. So firstly, we'll go over here to group type and change it to points because that's the attribute type that we would like to be affecting. So attribute will keep as color, but you can mirror any attribute here. We'll go down here to attribute mirror, and this is how you would like to mirror your values. So we would like to base it off of a direction. So we can set to vector mirroring, set direction to 0, and we'll go 1 on the y-axis. So as you can see, it has now mirrored our attributes. So it's taken it from the top, and from the origin of 0, which is, you know, in the middle, it's mirrored in a direction. So you end up with that. And, you know, this could be useful. I just personally don't use it very often. The fact that you can also use UVs is great, so you don't have to use just a vector direction. You can get quite in-depth with this. So let's move on. Let's see, what haven't we used yet? Let's go ahead and use an attribute interpolate. So let's drop that over there, and we'll need to plug some things into this. So, firstly, we can just drop a sphere. Let's make it a polygon mesh. And we'll give it rows of 50, columns of 50. And then for this attribute interpolate, you'll see that it has these two attributes over here, source prim and source prim UV. So source prim is a primitive number, and source prim UV is like a position. We can go and drop down a scatter node, plug your sphere into the scatter node, and then plug it into the first input of your attribute interpolate. Now on the scatter, if we go to output attributes, you'll see that there's this prim num attribute and prim UV attribute. And you can output these two. So what that's doing now is it's finding, if we go over here, we can take a look, it's finding which primitive this is coming from. So that's the source primitive, and where on the primitive the point has been scattered, right, based on UVs. So we have all of these, you know, primitives, and the points are being scattered, and it's recording source primitive and the source prim UV. Now what can we do with that? Well, the thing with attribute interpolate is that it allows us to stick these points to their primitives. So how is that useful? Well, you know, we can drop down a mountain, plug our sphere into the mountain. So we have this. And then we can go down here, we'll just decrease the octave so it's smoothed. And then over here in offset, we'll just put $T for time, so that it changes over time. Great. So now, this is where it gets interesting. If you take your mountain node and plug it into your attribute interpolate, take a look at the points that we've scattered. They move with that mountain, and they stay on the right point. So you might be saying, well, you know, why don't we just scatter after the mountain? So if we duplicate that, and then plug this into the scatter node over here, well, the issue is that you rescatter these points every time. And oftentimes you don't want that. You'd like these points to be remaining constant. And that's exactly what this does. All it's doing is moving points that already exist. So we can just drop a copy to points, plug this in over here, drop down a tube, plug it in there, and drop the scale 0.05 by 0.1 or so. Yeah, that should be fine. Put on some end caps. And then just make sure that we have some normals. So just plug it in over here, change that to points. And then we can rotate these. Which axis would that be? Yeah, there we go. So, as you can see, quite cool. We now have this. And this is, you know, just a very basic version of what you could be doing with this. You could use in an attribute wrangle, you know, a length function, and find the distance from origin, and make those points bigger as they move further away, or, you know, change their attributes so they change color as they move away. You can do all sorts of cool things with this. And, you know, these points just stay where they need to stay, and they don't resample or reseed. Honestly, this is one of my favorite things to work with, just because it's so simple, yet it just adds such a nice effect. So let's keep going. We're getting somewhere now. And let's try, what have we not done? Attribute from map. This is another great one. Super useful. You can drop a grid. And the best way to use an attribute from map, I found, is to actually define on your grid the correct resolution of the image that you're bringing in. So attribute from map calls in an image and then applies the image as a CD attribute onto a geometry. So we can just go over here, let's go to my H drive, tuts, and I've got this galaxy wallpaper image. And one thing that's useful to check is to actually go to that image, so on the H drive, tuts, and check the details. So properties, we have details over here, 2880 by 1800. So now we know the resolution of this. So all we have to do is make sure that our grid has a similar resolution, or else you end up with this. So for size, we'd like this to be the same ratio. So we can just go over here, and it's 2880 by 1800. So we can just go 28.8 by 14.8. Or was that 18? 18.0. Yeah, I think it was 18. Great. And rows and columns, we don't have to do, 2800. We can just do 1/4. We'll do 1/4 and we'll do 900, so half. And there you have this image now being cast onto your grid. So you have this grid, a whole bunch of, little cubes, little blocks, kind of like pixels. And then you can just attribute from map, and you end up with that. So what's that useful for? Well, what happens if we drop a pop net? We can make particles pick up these attributes. So just dive inside of this pop net, and we can switch off the guide, and we'll use the source scat onto surfaces. For birth, we can push this way up, maybe 250,000. And then just set its life expectancy super low, 0.1, variance of 0.2 or so. And then drop wind. So pop wind. We'll increase the amplitude to 1. And let's just see what that does. Play this back. So not enough points right now. We can increase this to maybe 500,000. And then just increase the life expectancy to 0.5 with a variance of 0.4. And you end up with this sort of swirling effect. So we can actually scale this down. Maybe it's too big. So we can actually do 2.8 by 1.8. Attribute from map. Still has the same sort of detail. Pop net. Set that back to the beginning. And play this back. And as you can see now, we have this, interesting swirling effect going on. And these attributes are being picked up by these particles. So, I'm sure you can find some sort of use for this. I've seen some people control other attributes, such as, velocity. So you can make these white areas have high velocity, so they are the areas that move a lot. And there's just lots of interesting things you can do with this. So let's try another one. And actually, let's do one that's less glamorous. Let's do measure. So measure measures various different types of values based off of a geometry. So for this, we'll just drop a sphere. We'll make it a polygon, or rather a polygon mesh. And plug that into our measure node. So we have this. So let's override this name. So currently we're outputting perimeter. So we'll just call it test. And then we can take a look at where it shows up. So it shows up as a primitive attribute and ranges between 1.03 and 0.58. So we can now drop a delete node and actually view what this looks like. So delete by expression, and we'll delete primitives, and we'll just say at test greater than 1. Just remove that semicolon. And as you can see, it's deleted the areas with the biggest perimeter. So all you're left with is everything below 1. So if you want to reverse that. So the highest value is 1.03, so less than 1.03. So that's the area with the highest perimeter. So you can see how useful that would be. And you know, there's other settings on here that are useful. You don't have to use perimeter, you can use curvature, which is, you know, immensely useful. If you drop down a rubber toy, you can find all of the crevices and things. So let's just remove this shader, duplicate this measure node over. We'll go over to curvature. And it's now a value between 0 and 1000. But this one, you'll notice, is a point attribute. And it's over there. It's ranging between, you know, 0.5 and 1000. So let's just drop down a color node. And we've still called it test. You know, we're just overriding the name so that we can find it easily. And over here, we'll go ramp from attribute. So let's take our test attribute. And we know its range is between 0 and 1000. And then we can drag this all the way over and pull this up. And I'm not sure if you can see this over here, but all these crevices are lighting up. And you can change this color over here to red. And I'm sure you can see how that could be, you know, a very cool effect. Say you just want to find the areas with the highest curvature, you want to find these crevices to maybe add some sort of grunge, procedural grunge, or you want to turn those into an emitter. You can easily go ahead and just in an attribute wrangle to find the areas and then give it an emission value and make those areas light up. And actually, I could probably show you that quickly if you want to make this an emitter. So you just say at emit int equals at cd.x times 1000 or 100, sorry. And we'll do v at emit color equals set 1, 0.25, 0. So that's orange. And then we'll just change this to white over here on our ramp. So we end up with that. Go over to our material palette, just drag a principled shader over. And control left click on camera, we now have a camera. We can go to render view, object camera 1, render. So there you have it, you know, very quickly, we now have these areas that are emitting. And, you know, that might be a bit crazy, so just multiply it by 10 rather. And I can see that all of these little crevices have color to them, and they're glowing. So a very useful effect, and you can just drop down an attribute blur so it doesn't have those, you know, weird raggedy edges. But that's just something I thought I'd show you quickly. So we can go ahead on to other things. Let's drop down a sphere. And this one's a bit of a weird one. We're going to be using attribute fade. This is something that you almost never see. So we'll just create a polygon mesh. And we'll make it a 50 by 50. Drop down a color node. Plug it into attribute fade. And let's give us a color of blue. Now between our color and our attribute fade, we'll also just drop an attribute wrangle, and I'll show you why shortly. So if you take a look over here, we have a couple of things. So we have this fade that's happening. It's very short, you can see it for maybe like 2 frames. And that's the fade in frames and the fade out frames. Now we're visualizing the fade. Currently what it's fading is it's creating an attribute called fade and it's fading it. So you can see that attribute over here that it's created. And it fades it in over 2 frames and out over 2 frames. So you can make this fade in over 20 frames and then make it fade out over 20 frames. And then it's easier to see. Alright. But there's other things that we can use over here. So if we go over here in our attribute wrangle, we can say at fade start equals 10. And then go at hold scale equals, let's try 20. And then we can go back over here and just those attributes that we created, we'll put them here. Fade start was the one, and then the other one was hold scale. So now if we check, it now doesn't change immediately because we have this fade start attribute. So it starts fading from frame 10, fades for 20 until 30, and then fades back down, right? So from 30 to 50 it fades. So what is hold scale? Well, hold scale, we have it as 20 over here, is the scaling factor for the amount of frames that you want to hold in between the two fades. So it fades in for 20, it holds for this amount, then it fades out for 20. But this amount we can set to 1, and that value gets multiplied by our hold scale, which is 20. And then you end up with this, where it holds for 10 because of our fade start. Holds for 10, so nothing happens for 10 frames. Fades in for 20. Holds for 20. Fades out for 20. So that's actually quite useful because we don't have to visualize fade. What we can do is we can drop an attribute wrangle and say at cd times equals fade. At fade. So the attribute that I just created. And now we're fading in and out of this blue. You know, this is a lot easier than using whatever other way you would use to do this. Like, you could probably use a ramp in an attribute wrangle, but I mean, you know, this is so simple. And it's so easy to control. So that's another thing that, you know, you don't see very often, but it's quite useful. So let's keep going. Let's try something with some VDBs. Let's do a sphere. Make it a polygon mesh. And let's actually increase the rows and columns quite high. So 300 by 300. Next, we can actually just duplicate this. And on the duplicated one, just drop that to 50 by 50. And then we can drop down a points from volume. So points from volume, create some points. And we can just drop the separation to 0.02. That fills out our sphere quite well. And let's just drop down an attribute VOP. Now attribute VOPs, they're just very useful for noise, like immensely useful for noise. Creating noise in an attribute wrangle is quite a pain. So this is where VOPs, well, this is where I use VOPs mostly, but we'll be going over VOPs a little bit more later. So in this point VOP, we can just drop down a turb noise. And if you visualize that, that's basically just, you know, a noise pattern that gets generated and it goes inside as well. That's quite useful. And we can just drop down a bind export. Bind export just creates an attribute. So as you can see, the moment that we plug this noise into our bind export, it creates this thing called palm. And we can rename that. So we can rename palm to lift, because that's what we'll be using it as. And now we have this lift attribute. So jump up a level. We can go ahead and use an attribute from volume. Now, the thing is, we currently don't have a volume, but this is quite nicely set up to be a volume. So we can just drop down a VDB from points, or from particles rather. Plug that in over there, and just change the values on here, 0.01. Change this to 0.01 and change this to 0.1. And then add an attribute onto this. An attribute that we'll add, we'll call lift. And the attribute that we'll call it from is our lift attribute that we created. So now if you go over here, and actually we don't want this to be a VDB surface, we want it to be a density. So now we can go ahead and plug this into the second input over here, and our sphere into the first input. So now it's transferring attributes, but it's transferring color. So we don't want that, we want lift. And let's actually do a transform. So let's transform our VDB, you know, across in time. So we will translate it on the x-axis by sine $FF. So now it just moves back and forth. Great. So attribute from volume fetches attributes outside of a volume and applies it onto a surface. So now if we drop down an attribute wrangle, you can see how this has worked. We can now say at p.y, or actually just at p, plus equals, let's push it along its normals, at n, multiplied by lift. And we have an issue there, just at lift. And as you can see, we now end up with this weird looking effect, where it's transferring this lift attribute, and it's a 3D attribute, because, you know, it's transferring from a volume, so it's evolving as it goes. And if you want, you can drop down an attribute blur before this, just affecting lift, and just give it a couple of iterations. And as you can see, it's quite interesting actually, the sort of effect you can get by using a volume instead of using an actual surface, because it looks as if it evolves over time. So as you know, this is just moving back and forth based on our sine wave. And then it's adding this lift attribute, and we're adjusting the position. So this is a lot like an attribute transfer node, except it's working, you know, in 3 dimensions, as opposed to just from surface to surface. So let's just copy over this one sphere that we made. And let's see what else we can do. So let's do a very basic one. Let's do paint. Paint is another extremely useful tool for, you know, art direction. Sometimes you don't want things to be procedural and you would like to control it yourself. So for us, we'll just set the color of our brush to black, and then go over here to your show handle, right? And this allows you to paint onto a surface. So mouse wheel scrolling up and down changes radius, and then you can paint onto the surface. So if you just do something like this, then, you know, I don't know, maybe some sort of pattern. And then we can just go ahead and do something similar to what we did before, where we just push it along its normals. So we can say at p plus equals at n times at cd dot x. And then we'll just multiply this by like 0.1. So it pushes it slightly. We can drop a VDB from polygons, plug this in over here, and we'll change voxel size to 0.01. Duplicate this over and bring in the original geometry. Maybe do a VDB combine. Plug one into there, that other into there. And then we can just do, let's do SDF difference. So now we can just drop down a smooth SDF. I know I'm using a lot of VDB stuff, but I'm just looking at this, it's starting to look kind of cool. We can convert VDB back to polygons. And, you know, that looks pretty cool. Looks like a Sharingan, actually. But the whole thing with this is, this gives you more control over what you can do. I mean, this is now an interesting shape that's very difficult to get any other way. So, paint node, very useful for things like that. And so, let's just go over one last thing. Let's go over, let's see, what haven't we gone over yet? I'm not going to go over all of these. Some of them, you know, you'll never use. Some of them are just, you know, not that impressive and very, very situational. So let's actually just go over how to properly use VOPs. So we can just duplicate our sphere over here. And let's paint on it again, actually. Let's paint. Change this to black again. And we're going to do a very similar thing from what we just did. And let's just draw on here, just maybe a face. Okay, and let's drop down an attribute wrangle. Once again, we'll do the same thing we did earlier, at p plus equals at n, and then we'll do times at cd.x divided by 10. So that's the same as times 0.1, it just looks neater. And there we go. Pushes those surfaces out. Just put an attribute blur before that, so it looks a bit smoother. CD. There we go. So we have this little thing over here, and what we've done over here is we've said at p, so our position. Let's add our normal direction, which we have over here. Actually, let's just add a normal node, just to make sure nothing goes wrong. It's always better to have these things plugged in. So add normals to points. Great. So we're adding to our position based on our normals multiplied by at cd.x. So cd.x we know is 0 in the black areas, and then we're dividing it by 10. This whole thing is being divided by 10, just because if we don't, it's just pushed out way too far. So we can just take a look at it like that. Now, one thing with attribute VOPs that a lot of people don't realize is that it's run by vex. So when you drop down an attribute VOP, you can exactly replicate what we've just done in this attribute wrangle with the nodes of an attribute VOP. So let's dive inside of the attribute VOP. So what is the first thing we did? Well, we added to our p-value. And what did we add to it? Well, we added n. But not exactly just n. We multiplied it by things. So we can drop down a multiply. And we multiplied it by the x value of our CD attribute. But this CD attribute is a vector, so we have x, y, and z, but we only multiplied it by our x value. So you can drop down a vector to float. And so that's x, y, and z, value 1, 2, and 3. So we'll take x, which is value 1, multiply it there. And then what did we do? Well, we divided it by 10, so divide constant, 10. And then that's what we set our p-value to be. So jump up a level, set your display flag here, and look at that, nothing changed. That's because this is exactly the same as this. These two things are exactly the same. This is just, more visual based. I know a lot of people prefer to use VOPs. Personally, I like vex, just because I feel like it's cleaner, as if you can, fit more with less. And the thing is, VOPs are extremely useful still. There's a lot of things where the code can be quite complicated, and VOPs just simplify it. Like, this is a pretty simple piece of code, so it looks complicated in VOPs, but when you get to complicated code, it becomes a lot easier in VOPs. And here's something a lot of people don't actually know. If you go to your geometry VOP output, you can actually go over here where it says vex or VOP options and say view vex code, because Houdini actually generates all of this code. And these are all, Houdini generated things. You don't need to worry about that. It's just, this is what the software produces. You can see here, it says code produced by Geometry VOP Global 1. So that would be this big node in the beginning. So those are just all the attributes that it creates. And if you keep going, you can see code produced by vec to float 1, that over there. So what is it doing? Well, it's saying VOP vec to float. So that's a piece of code. That's a function that VOPs use. It takes your CD attribute and splits it into 3 values. Cool. So we have fvol1, which is our x value, and then our multiply is creating a product, right, of our n value times our x value of our color attribute. And then we're saying scaled, so this is created by our div constant, divide constant, is our product, so what's coming out of our multiply, times 1 divided by 10, which is the same as dividing by 10. So then it goes over here and says the sum, which is another attribute that it's created, is equal to p1, so our position, plus scaled, the thing coming out of divide constant. And as you can see, over here we have vector underscore p equals sum, because we're taking this sum value and exporting it as p. Right, that's what it's doing there. And so VOPs are just a more visual way of understanding Vex. Now, of course, there's some things that VOPs are much better at, like noise, but I mean, you can tend to avoid Vex if you know VOPs, or, you know, vice versa. And of course it's useful to know both, but you don't have to. The thing is, if Vex scares you, or if you're not the type of person who enjoys coding, you know, there's VOPs for you. So that's all we're going to look at for now. In our next tutorial, if you like this, we'll create more. I mean, there's so many nodes to go through. It could take a while, but if you would like me to go through the rest of them, then I'll be glad to. But that's all for this tutorial. Thanks for watching. Also, a special thanks to our patrons. They really help keep this going, thanks to their support. So be sure to like, subscribe, check out our Patreon, and we'll see you next time.